What's up?
Handling it.
Yeah.
That's about it.
I'm here.
That's exactly right.
There's only
Feel
gap
like you're
committee
missing.
meetings.
A lot of work right now.
All right, let's get started. So we're happy to have Rupert Klein joining us this week. Rupert got his PhD in 1988 in mechanical engineering from Aachen University in Germany, followed by a couple of years as a postdoc at Princeton. And for the last 25 to 30-ish years, he's been at the University of Berlin in Germany. He is a chair in scientific computing and also has had, or maybe still has an affiliation, no longer anymore, with the Potsdam Institute of Climate Impact Research. He's won numerous awards. Two examples are the Leibniz Prize, which is the top science award in Germany, and also he has been a 3-year fellow at ECMWF 2 different times. So thanks for coming, Rupert. Take it away.
Thank you very much, Sam and Leslie, for having me, and thank you all for the opportunity to present at your Atmosphere Ocean Science Colloquium. And I'm going to talk about the development of triple-deck boundary layers that extend the classical quasi-geostrophic theory and give new insights into the regime of incipient hurricanes, as I will explain. And there's a number of people whom I would like to mention who have worked with me on this. Eileen, Patrick, and Anthony worked with me on the 2012 theory of strongly tilted vortices. That will be the middle part of the lecture. Ariana and Tom have been doing 3D simulations to corroborate the asymptotics. Sabine, Piotr, Burlan, and Lisa and Stefan are all co-workers on this in one way or the other. And with Lisa and Stefan in particular, we did the extension of the quasi-geostrophic theory that I will present first, as coming up now. And the German Science Foundation has paid lots of my bills in various programs, and I was a fellow at the ECMWF, and that has given me a lot of a background in the real life of meteorology. So here is our extension of the classical theory, and this DL in the middle here, which is the new boy on the block, kid on the block, is the diabatic layer, and I will explain what I mean by that. When you look at the diurnal circle, diurnal cycle over basically cloud-free region on large scales, then when the sun comes up in the morning, you typically can see convection building up. Starting from the stable boundary layer, you start mixing vertically, and then by noon or so, or a little later, you have a mixed layer that might reach up to 1 to 2 kilometers in height or even higher. And in particular, the potential temperature, the virtual potential temperature, takes profiles like this. It's unstable in the boundary layer down here. It's nearly neutral over quite a stretch, and then higher up it returns to its background stable stratification. And so you can see that in the lower 3 kilometers, there's a lot of action here that is different from what you would expect to happen up here, where things are basically stably stratified and stay stably stratified. A similar picture arises in terms of separating the upper and the lower part of the troposphere. When you look at the typical moisture content, specific humidity here in this diagram, over the pressure, i.e. the height essentially, and you find out here at 500 hectopascal, that's about 3 kilometers, and most of the moisture is actually seen in the lower parts, lower 3 kilometers, and up here, due to Clausius-Clapeyron and its exponential temperature dependence, the moisture content higher up is really very small. So again here, most of the moisture stuff is happening in the lower 3 kilometers, as it seems. Now what has all this to do with quasi-geostrophic theory? Here's a diagram that shows potential temperature, the dry potential temperature versus the height. And the key assumption in deriving the quasi-geostrophic theory is that the potential temperature has a background profile that only depends on the vertical coordinate, here represented by the dashed line, and it is a deviation of the reference background or bottom ground temperature of order of the Rossby number. Epsilon here, you can think of it as the Rossby number. So it's of the order of the Rossby number, and this stable background stratification, it depends only on the vertical and is time independent. Deviations from it, which make up for the dynamics in the QG theory, are one order up in the theory. So some people say one order down, they are one order of magnitude smaller than this background stratification, so they are order Rossby number squared only. And that means in particular that in the lower 3 kilometers, you cannot overcome this stable stratification by the dynamics of the flow. So QG doesn't describe the situation that I just had on the other slide, where you have this stable stratification, neutral stratification over quite a distance, and then return only higher up to the background stable distribution. And this was bugging us, and we said, something is going on. It should be interesting. All the moisture is here, so that when we want to study moisture effects seriously, with all their strengths, we need to do something about that theory. And what it is introduce an intermediate layer that's not like the Ekman layer by a factor of the Rossby number smaller than the scale height or than the tropospheric height. This is the Ekman layer down here. But it is of square root of epsilon in height. Here it is. The square root of epsilon of the Rossby number smaller than the scale height, while the Ekman layer is another factor of square root of epsilon thinner. So we have a new intermediate layer height within which we allow, by the asymptotic ansatz, to deviations of the potential temperature to be bigger than they are here, namely in size comparable to the difference across of potential temperature across this height that you would see in the background. So we assume specifically that these perturbations can completely topple the stable stratification, change it into neutral or even unstable one. Okay? And then basically the rest is cranking the asymptotic crank, and I don't want to bother you with the details, but rather discuss ramifications of what's coming up and juxtapose it against the quasi-geostrophic theory. So here's the recap of QG theory, QG Ekman theory. Basically what we have is the transport of potential vorticity, which is the horizontal advection of PV, that's typically called Q in quasi-geostrophic theory, and it might be driven by a source term, heat sources, and we're specifically interested in diabatic effects, so I include them here as a source term on the right-hand side. So when you extend QG from the classical adiabatic setting to include heating and cooling terms, you get an additional term like this. So this is the dynamics or evolution of the PV, potential vorticity, and you can reconstruct a pressure field from this Q field here. Beta Y is the beta effect of the Coriolis parameter, and you can reconstruct by solving an elliptic equation. This is basically the standard elliptic pressure equation that you have in the quasi-geostrophic theory. Notice here you can already see on the right-hand side here we divide explicitly by the background stratification. So if that was neutral and i.e. 0, we'd be in trouble. The same happens in this stretching term. N squared is the Brun-Belisala frequency, which is proportional to the slope. So if n was going to 0, something has to happen. QG doesn't like that. That's another indication that something needs to be done if you actually want to deal with neutral stratification somewhere in the other. Okay, then there is an interesting bottom boundary condition that you have for solving this equation. Later on, I will just use far-field decay conditions so that the pressure goes to a constant in the distance, or we assume periodic conditions. At the top, for now, we assume a rigid lid as an approximation for the tropopause. This can be extended, but we don't do that here. So the main boundary condition we're talking about is that at the bottom. And the bottom boundary condition is a Neumann condition, meaning the vertical derivative of the pressure, d pi dz, at the bottom, evolves in time, so it has its own time evolution equation, according to this right-hand side, which consists of a driver by the heat source near the ground and the vertical velocity near the ground, which you have to derive from the Ekman layer theory. And in fact, without going through the details of the friction layer equations, the net effect, the net outcome of the Ekman theory is that you get the vertical velocity at the ground of QG theory from that derivation, from these derivations. So when you go out of the Ekman layer, you see, as due to convergence forced by the pressure field that lasts on the boundary layer, you get a convergence or divergence, and that produces a vertical velocity coming out of the Ekman layer, and this is the boundary condition for what happens at the ground in the layer above in QG. So that's the classical theory. This is called the Ekman pumping velocity, and we will talk about this later again. Now, the logics of the coupling is as follows. It's very straightforward. You have to solve this elliptic equation over here. Then when you have that solution and you have the pressure field, it exerts a pressure on top of the Ekman friction layer. It induces a flow over here, and that flow again produces the vertical outflow of the layer, and that's the Ekman pumping. This is how these two layers are coupled, and once you're able to, which analytically you are, once you connect the outflow here to the pressure field by the Laplacian, the horizontal Laplacian of the pressure, then the system is closed. Okay, so the logics of the coupling is by pressure is imposed, induces a friction layer flow, and that again produces an outflow, and that gives you the bottom boundary condition, evolution of the bottom boundary condition for the for the QG layer. So far so good. Now how do we move on for the diabatic layer? Well, in the diabatic layer, what we do is we keep basically the order of magnitude of horizontal and vertical velocity and the pressure field. These indices up here are all indicating at what power in the powers of square root of epsilon in the expansion these guys appear. This is all, the details are not important. What's important here is that all these variables, horizontal velocity, vertical velocity, and pressure, all appear at the same perturbation order as in QG, but the potential temperature is not theta squared or theta 2 anymore, it's theta 3 over 2, so this is by 1 square root of epsilon bigger than the perturbations we are allowing for in QG. So that's the key difference. The other difference is that now the diabatic layer doesn't scale or is not described by a vertical coordinate that stretches from the ground all the way to the troposphere, but by a stretched coordinate that's rescaled by square root of epsilon. So basically, you're describing this thinner layer of height square root of epsilon times the scale height. And this is important because now, since these variables are all having the same order of magnitude, you still get geostrophic balance. So the horizontal gradient of pressure via balances or is balanced by the Coriolis force, and this gives you the usual relationship between horizontal velocity and the gradient of the pressure, horizontal gradient of the pressure field, as the same as you have it in QG. Hydrostatics is still valid, even in this thinner layer, but it's now driven by a bigger potential temperature perturbation, which means that this pressure at the same order as in QG can non-trivially be changed when you go from the QG layer all the way down to Ekman. So you get another change of the pressure before you reach the Ekman top, where then the Ekman layer flow is imposed. And that's the key difference in that theory. So we still have hydrostatics. We also have a mass conservation law, and here the difference is that first, because we're in a thin layer, the unelastic constraint reduces to just the incompressibility. meaning horizontal divergence plus vertical divergence of the velocity itself is 0. But owing to the geostrophic balance in the horizontal velocity or horizontal momentum equation, the divergence of the horizontal velocity is 0, so that the vertical velocity actually is constant throughout the layer. That makes life easy, because what it means is anything that comes out of the Ekman layer in terms of vertical velocity is simply handed through to the bottom of the QG and keeps Ekman pumping it there. Okay? So what's the logic? And then importantly, this large perturbation potential temperature evolves according to horizontal advection and whatever you have in terms of source terms over there. And so if you have strong enough source terms, you may mix, for example, and get a neutral stratification. So what's the logics here, the logics of the coupling? It is, again, the QG pressure is imposed on top of the boundary layer, which is now the top of DL. That is transformed by a hydrostatic balance to some different pressure, which is the pressure at the bottom of the diabatic layer. So you are changing the Ekman layer flow, but with this new, different Ekman layer flow, you produce an Ekman pumping. This vertical velocity is handed up to the bottom of QG, and you get this modified pumping, which is not the same that you would see if you had the QG pressure right on top of the Ekman. So this is where really an order 1 change of the QG flow up here can be established.
And that's where you use hydrostatic, takes the constant theta in the mixed layer. Is that right? Is that how you go from the pi QG to pi DL? You know, the pressure
pi QG is basically, they have to match over here. So this is constrained to be equal to pi QG.
At that top.
Basically in a overlap region. And then kicks in the larger variation of the potential temperature. And you get hydrostatics changing the pressure again before you reach the Ekman.
Okay, thanks.
Yeah? Okay, good. And the key new aspect is that, so the logics obviously is different, and you can get a very different QG flow due to diabatic effects in that layer. Another way of looking at it that makes really clear that we have different physics going on comes from a PV perspective, of the potential vorticity perspective. Namely, when you look at the leading order contribution to Ertel's potential vorticity, in the QG theory, it is dominated by the vertical component of vorticity. So only by the horizontal rotation. That makes up the dominant part of PV in QG theory. Here, it turns out, as we will see later, the horizontal parts of the vorticity can play as big a role as the vertical vorticity, owing to this different scaling of the potential temperature perturbations. So suddenly you have PV coming from any direction of the vorticity that plays a role in setting up the flow, if you wish, and to interpret it that way. So this kind of stuff cannot be described in the framework of QG. That's clear. Right. And here's a simple example that one can basically almost analytically solve, which is an application that Roger Smith and his students have worked out, and they labeled it a spin up of a heat flow. What is it? Roger is an Australian, so he has an interest in what happens over Australia, and you can have the heat basically bombarding the large plains in Australia, and then you see from the morning to over the day a huge low spinning up, pressure low, even though everything is clear sky and very hot. That's a heat low. And they basically did numerical simulations to demonstrate that this would happen in a 3D code. And here it happens in our new theory. So what do we do to set this up? We model small-scale convection by a diabatic source term that is designed such that coming from a stable stratification of potential temperature at night. We basically mix the potential temperature vertically to a neutral state over 12 hours, so that later on we have, at some height of 2.5 kilometers, we have a neutral stratification underneath and the stable stratification on top. This is our model for this convective heating that takes place when the sun is shining onto the surface. We do an axisymmetric distribution of this heating, and we modulate it in the radial direction by a Gaussian hump, right? And you can see the effect of this here, which is basically after 48 hours. This is what our level sets of potential temperature in the RZ plane look like. You can see here the stable stratification, and under this Gaussian hump, you basically have neutral stratification modulo what happened in between 12 and 48 hours. Right? So we basically lift this Gaussian and have a mixed layer underneath. And then you can actually solve these equations analytically almost, except you have to solve this elliptic pressure equation. And we start from a, where did I say that? Initial condition is a stably stratified atmosphere at rest. So PV is completely zero to begin with in the QG domain, and since we have no heating up here, PV will stay zero up in the QG part. Okay, here's the solution. So after 12 hours, that's when we have basically had our cosine function do its job and the heating stops. The mixed layer has established. We see, in fact, a cyclone under this hood having developed in the diabatic layer, and it circles around. 12 hours later, the time-dependent bottom boundary condition for the QG theory has done its job, and it has started to evolve a flow in the QG part. Okay, so, and what it actually does, it spins up an anticyclone. And it keeps doing so, the anticyclone becomes stronger, and the cyclone underneath loses energy to it, and in the end, this is more or less, we go this way around the clock. This is after 48 hours, this is basically the steady state that's reached afterwards. Okay, so this is the composite solution, which is basically pieced together according to the rules of asymptotics to show one uniformly valid solution throughout the entire domain. And if you want to see what the individual solutions to QG, DL, and Ekman look like, this gives an impression. So if you only take the quasi-geostrophic solution after 48 hours, it looks like this. It's just an anticyclone. But if you then add to that, superimpose it with the diabatic layer solution, you see the cyclone underneath, but this has a zero slip condition down here, so you need the friction layer on top in order to see the no slip condition at the ground. So this is the composite solution we get in the previous picture. Okay, so now that finishes part one of the talk. Yeah, that's okay. Finishes part one of the talk. And I think there is some life after retirement for QG theory in some sense. With this addition, you can address a lot more interesting phenomena than you can with classical, and it might give rise to interesting follow-up.
Now that shear zone in the combined is going to be, is it in geostrophic balance with the temperature gradient that develops when you have that heat bump?
Yes.
That's pretty neat.
Yes. Mm-hmm. Exactly. That's all. The question is, when I go here, obviously you have a radial potential temperature gradient, and that basically gives you a thermal wind, which is exactly what that vortex is. Yeah? Except for the Ekman effect. Yeah. Okay, good. So that was this part. Now let me talk about part two, which is strongly tilted vortices. So this goes back to a 2012 paper with Eileen Peschke and the other colleagues, and to recent work with Tom Gerfel and Piotr Smolakevich and my former students. And it starts off from a paper by Dunkerton and colleagues in Atmospheric Chemical Physics 2009, who did the following. So they went to look at these baroclinic waves that come from Africa and travel over the Atlantic. They hopped onto a moving frame of reference to follow one of the troughs of these waves, and then monitored the observed, or there are 5 velocities, if I recall correctly, in this region, in the moving coordinates. And in these coordinates, what you can see is, for example, the horizontally divergent part of the velocity field creates an inflow near the ground and an outflow at the top. And I'm showing this only because it very nicely shows these developing, almost axisymmetric flows near the ground and at the top, but it also shows, and that's important for building the theory, it also shows that the center near the ground, the red dot here, and the center at the top, the other red dot, are, in this case, 200 kilometers apart. So that means these vortices in the incipient stage, they are pancakes, very flat, 12 kilometers at height, and have their centers separated by 200 kilometers. So the vortex center is tilted, it's almost lying down. So it's nothing like an almost upward vortex, which you could treat by perturbation theory around a vertical straight vortex. It's not possible. So we wanted to capture this regime because this transition from tropical storms to hurricanes is still theoretically the most interesting and uncharted terrain. Also, since we are talking about transitions, we don't want to do QG, because that basically gets us to Rossby number is very small, and then hurricanes, in contrast, have a very large Rossby number when they are fully developed. And so the natural regime to look at is what is called gradient wind regime, where the pressure gradient in the radial direction in our axisymmetric system, the Coriolis force, and the centripetal acceleration, they're all of the same order of magnitude and balance each other at leading order in the horizontal momentum balance. So that's what's called the gradient wind balance, and it's by definition, asymptotically speaking, the Rossby number here in this regime is order 1 and not small. Right? And so this is what we are after. Okay, so how do we set up an asymptotic expansion? The key ideas behind it are as follows. We want a center line that represents this possible tilt of the vortex. We want to mimic that basically once the vortex starts seriously spinning up, it really looks, at leading order at least, axisymmetric in every horizontal slice. So at every height, when we slice through the flow, we want to see an axisymmetric flow modulo small perturbations, relative to this tilted center, wherever it is at this height. Okay, so this allows us to look at axisymmetric vortex flows with different positions at different heights. So that's a very strongly tilted flow. And then we want to set up the velocity and the radial scalings so that the physics of the QG flow in the vicinity and the spin up of the vortex match each other. And how do we do that? Basically, we want small Rossby number in the vicinity, that's QG basically. We want, and that should be changed from order epsilon to order 1 in the vortex, so we want to have the gradient wind regime and not QG. And we want the circulation in the environment and the circulation in the vortex to be comparable. Why is that? The folklore of spin-up of hurricanes has it that basically rotating air from large distances is pulled in, and then by the pirouette effect of ice skating, basically by angular momentum conservation, you get that spin. So basically, it is a different way of saying the same as the Helmholtz circulation theorem. You have a line of marking particles around the vortex. That line has a certain circulation, and when you pull that line inwards, then the circulation remains constant. Since the length becomes smaller, the velocity has to go up. So this is the second requirement. One requirement is Rossby number changes from epsilon to 1 and circulation stays constant. Well, you have two parameters to adjust, namely a length scale, that means change the radius from the QG synoptic scale to the radius of the vortex is one parameter, and changing the velocity magnitude is the other. And what you get is, you get naturally, by these two constraints, the square root of epsilon being the key variable, the key perturbation parameter. You need to scale up the velocity by 1 over square root epsilon, and you need to scale down the horizontal length scale by, again, a factor of square root of epsilon. Notice that the synoptic scale in this notation is the scale height divided by epsilon squared, so this here is by a factor of square root of epsilon smaller than the synoptic scale. That uniquely fixes the regime, and now you can start cranking the crank again, and again, I don't want to bother you with details, but show you the key results. Okay? So the key results is we get a theory that describes a fully three-dimensional structure of vortical flow. It includes the vortex motion, meaning the vortex centerline motion. It includes an evolution equation for the primary circulation, for this main rotating flow. And we mimic the effect of adiabatic, of moist processes by diabatic heating and cooling patterns, just as I explained it earlier for the QGD electron theory. So for now, that in that theory in 2012, this is what we did. So we mimic the moist processes by cooling and heating. So here's just the fact that we get an evolution equation. I could explain all the terms to you, but let me not do that. Give you the key idea here, the key important aspects of it are, you have one part of this motion of the centerline position that looks like a slender filament, slender vortex in fluid dynamics moving all by itself, not being connected to its own vortex core. That's typically called the local induction approximation. It's very similar to that. But there is a more interesting part, which is represented by the symbol psi here, and it is a function, or better a functional, so an integral over the radial distribution of the primary circulation, the entire core structure of the vortex, the centerline geometry, and of the diabatic source trans. All of these guys play a role in pushing this vortex around. Right? So it's strongly coupled to its own internal evolution that depends directly on the heating and on the centerline geometry. So there is a coupling between vortex core evolution and the tilt, this meandering centerline evolution. And if you switch off the heating and you look at the equations and you try to find an exact solution where you can actually say, okay, this is what it should look like, you find actually that in this case, when you switch off the heating, the centerline moves under the dynamics of a linear Hamiltonian system. And you find eigenmodes of it by basically doing eigenvalue theory, and it describes a precession of the vortex, so it's a cosine-like function of the centerline, and it moves around at constant amplitude, does a slow precessing motion. That's an eigensolution in this asymptotic theory if there's no change of the core structure. And here is a comparison with this solution from the asymptotic theory with 3D simulations, which Ariane and Tom developed in their thesis. And you can see here that it's not perfect, but you get this precessing motion. The precession frequency is off by a factor of 20%, but since square root of epsilon is about a third, that's within the range of what one expects in terms of just the leading order theory, it's acceptable. So we get qualitatively at least this precessing motion for a rather long time.
So Rupert, your heating and cooling is fixed. Where's your heating?
What
Heating and cooling is fixed. What's your heating and cooling again? You said
the heating is zero.
In
right
this
now,
case.
In this case, the heating is zero.
And then when you add it, how are you going to add it? Is it fixed?
I'll show you.
Okay.
So right now there's no heat.
Okay.
Good. And here is the equation for the primary circulation. So this u theta is the flow around the circle at each height. And these terms here are all what you know from standard axisymmetric balance, momentum balance. It's essentially angular momentum conservation that you have here. That's well known. And if you have a radial flow induced by the heating process, radial and vertical flow, then you can pull in mass from the distance and you can spin up the vortex. That's the usual way of looking at this. But if you have a tilted vortex, there appears a right-hand side which has a positive factor here. This is in a cyclone, this is positive. And the UR star is an apparent radial velocity that now, basically, depending on its sign, can either spin up or spin down the vortex, accelerate or decelerate. This UR star turns out to be the following. Take the circumferential average, theta here is the angle in our polar coordinate system at every height. Take the circumferential average of the vertical velocity times basically the tilt vector of the center line. Now, in the polar coordinates, the tilt vector is represented by this combination of sine and cosine functions. So when you take the circumferential average, you pick out the first Fourier modes of the vertical velocity. So those will be the relevant ones that play a role here. And if this happens to be non-zero, you get a UR star, and you can spin up or spin down the vortex. And the vertical velocity itself consists of two parts. One is basically what is called adiabatic lifting by Frank and Ritchie. I think that paper came out in 80-something. And Sarah Jones simulated in 95 vortices, adiabatic vortices, where she could really nicely see a first Fourier mode vertical velocity due to the tilt of the vortex, but it so happens that this goes with the normal, the 90-degree rotated tilt of the vortex. So when you put it in here, this cancels upon averaging. So this has no contribution to the UR star. So this is why you don't see any effect here in the strength of the vortex. It stays the same, it has no change. But when you have heating, you see what an effect on the vertical velocity is well known from the weak temperature gradient approximation. Simply heating drives mass up or down, so that mass always tries to stay in its environment of neutral buoyancy. That's basically what it says. So you have a stable stratification, the mass wants to move up when it's heated and wants to move down when it's cooled. And that's basically where that term comes from. And now depending on where this first Fourier mode of the heating points, in which direction it points relative to the tilt, you can have any sign of the UR star and a maximum magnitude that is the Q mode divided by theta by the background stratification times the tilt vector. Right. And so Olivier Paulouy, when he heard this first, we didn't have that slide here yet, and he told us, can't you somehow relate this to Lorenz's available potential energy theory? Lorentz developed this rather general theory that tells you how heating is turned into added additional potential energy and kinetic energy, and how this exchange takes place. And so we went back to our formulas and cranked the crank and found out this is the conservation law for kinetic energy of the primary circulation if there's no heating, and it's a conservation law. If we have heating, the interesting first observation that we had is that the axisymmetric part of the heating and the perturbation of potential temperature play as big a role for the acceleration or deceleration or the change of kinetic energy of the vortex as does the scalar product of the two dipoles of the heating and the potential temperature perturbation. as it should be according to Lorenz's theory. So the non-symmetric and the symmetric effects appear at the same order in the theory. That's important. But in addition, you can basically, you can see that they both enhance or decrease the kinetic energy. And this is basically what we found. And later on, you will, at the end of this part of the section, you will see that we find a configuration where this is the dominant part here, and it basically spins up the vortex indeed, and this has a negative effect, so it partly eats up the acceleration coming from the symmetric part, but when in this regime where this is negative, it can stabilize the vortex. So I mentioned earlier that the heating can have an effect on the centerline motion. And in the regime where this is negative in this balance equation, it tends to pull the vortex upright. So that means when there's a shear, this term effectively can basically stabilize the vortex against the background shear. You will see that later on. I'm anticipating that here, and I will remind you of this in a minute.
Does that allow you to make an estimate on how much shear could be navigated in that way based on how much heating would be required to do it?
If you remind me of that question, if I don't come back to it later, I have a partial answer.
Okay.
Good, and here we go. So the theory that the hypothesis that Tom and I developed, discussing with colleagues Paul Rieser and others in Florida at the Hurricane Research Center, was the following. What you often see, and this is much discussed in the context of rapid acceleration of hurricanes, is that there's a background shear. A hurricane is developing, and for quite a while it's sitting there and developing at convection down shear left, as they always say. So shear direction is this way, and then convection is developing down here. According to our theory, what should happen is the shear tilts the vortex. The tilted vortex has a self-induced precessing motion, so it starts rotating out of the shear, and then this heating can, as it turns out, this negative, so it can actually stabilize this shear, the rotated vortex can stabilize it against further shear. And then you can have a quasi-stationary situation under which the vortex is basically developing for a while and remains quasi-stable. And the idea here is that convective updrafts replace what we previously modeled as heating and cooling effects. And I did the basically first assessment in a multi-scale asymptotic theory of what an ensemble of updrafts would do, and it turns out, fortunately for us, that this W here, which comes from the heating, if you replace it by the mean mass flux over the ensemble of convective events, it has exactly the same form. So you replace this contribution of the vertical velocity by the mean over the convection. This is like a mass flux parametrization, right? Then it plays the same role and it generates a UR star. So great, our theory still holds up if we really have convection there. But of course, and now I come back to your question, in order to see how much strain, basically, or shear this guy could survive, we have to have an answer of how much outflow, how much mass flux in the convection is produced or provoked by the tilted vortex. And that's why we need a boundary layer theory, and this is part 3 of the lecture. But before I move to that, Tom modeled this effect more or less qualitatively, looking at data and at the observations, and he used the asymptotic equations to put a initially vertical vortex, subject to shear now, and here is the centerline evolution in a 3D picture, from going from black to red as time evolves. Here is a top view of it. You can see that the vortex moves in a certain direction, it stretches out and gets tilted, but it stabilizes, as you can see. So this is according to what I just said. It basically moves this way, then it rotates slightly, and then you can see the shear is first tilting it this way, but then it starts rotating around. And it stabilizes there. And you can also see here, in this double diagram, where on the left you have the u theta maximum. That's the maximum wind of circulation. It actually increases continuously the whole time while this is going on. So it goes from 10 to 20 meters per second. Interestingly, the red curves, where the scale is on the right-hand side, this is the power input you get from these two terms. This is the mode 1 power input, this is the mode 0 power input, and the sum is the solid line of the two. You can see that the axisymmetric convection, the part of the convection, it always produces positive energy input. The asymmetric part actually drains a lot of energy, and in fact the entire source of energy is negative for a while. This is the 0 line. So for quite a while, the total kinetic energy of the vortex decays, but due to a rearrangement of mass inside of the vortex, you still get an amplification of the maximum velocity, until finally the asymmetric part gives up. It's now very small, and the total, the sum of the energy inputs from the symmetric and antisymmetric becomes positive again, and then the entire vortex spins up, and the total kinetic energy also goes up. So this seems to be actually a model that mimics what observations show. That these vortices stand there for a while, and then after a while they go off. So we hope, of course, to implement a more serious boundary layer / convection model in order to have the full evolution, including this rapid acceleration, but that we don't have yet. And with that, I get to the last part of the talk. It's relatively short. I think that's really good. It's relatively short. What do we do? Now, we have the tilted vortex theory for the upper part, and now we introduce, just as in the first part of the talk, a double boundary layer, which has a friction part here and the analog of the diabatic layer in the QG theory. But here we call it differently. The name is convection controlling layer. You see why, you see it in a minute. Okay, so we do an expansion, and again we have the square root of epsilon, which basically dropped from the sky in the QG theory. We have it here coming in naturally. Remember, we had to rescale by square root of epsilon to go from the QG to the gradient wind regime to focus on our vortex. So square root of epsilon is a natural expansion parameter in the setting. And now if you look at the scales of vertical velocity in all the three layers, it's just as in the QG Dirac-Ekman theory, the vertical velocity stays the same order of magnitude all the way through, which is nice and consistent. The radial velocity, however, is very small up here. It is of order 1 in the convection controlling layer, and it's of order 1 over square root of epsilon, that is comparable to the main rotation velocity in the friction layer, which is also a very well-known effect in these hurricane boundary layers, that you have tremendously strong convergence near the ground. Okay. So this is why it also seems natural to have an intermediate layer, because you nicely couple or go through 3 orders of magnitude of radial velocities from the bottom all the way up. Okay, so what do these equations look like? We get standard boundary layer equations. You find them in many papers. This is basically radial momentum balance, angular momentum conservation for the primary circulation, divergence constraint, and then here's the definition of this angular momentum variable, which also comes in by a nonlinear source term in the radial momentum equation. Interestingly, Mike Montgomery writes in a review paper on boundary layers for hurricanes that this well-known effect that you can have an overshoot of the primary circulation, so the maximum circumferential wind actually appears in the friction layer in a hurricane, which is sort of a surprise because you would think, well, there's friction, it's all slowed down. But no, it's not the case. The reason being that air, here's a radial velocity plot, air comes in from distance, and by angular momentum conservation, it spins up the primary circulation, and it actually overshoots and then turns around again. This is positive radial velocity, so actually the parsecs make a transition going in and then going out again. And that's why you actually get the maximum of the circumferential velocity in the boundary layer. That comes out nicely here. So you have a turning point in the secondary circulation, and that leads to what is called supergradient velocities. An interesting aspect numerics-wise is that I haven't seen anybody solving these equations as they are. What I have seen is, for example, Rich Rotuno's work, where he basically puts in a radial diffusion. I don't know really why, but they seem to need that to stabilize the numerics. And Mike Montgomery says you cannot actually have a turning point because it's like a Prandtl boundary layer where the boundary layer theory breaks down at a stagnation point. Turns out, due to this momentum source term here, which makes the equations, when you drop the friction, then you make them into an oscillator equation, nonlinear oscillator equation. The natural part of the solution is a turning point. There's no problem in getting it. But you have to carefully discretize the advection terms here, which is 2D advection in the radial and the vertical, by accurate higher order upwinding. That's how we did it. You could use similar Lagrangian or what have you. You need to carefully discretize the diffusion and the source terms, but then you can very nicely solve these equations all the way to convergence. Then we get these turning points, etc. Then you get to the convection controlling layer, and what you get is an Eliasson balanced vortex model. It's a very well-established theory in this area, but it was never looked at in the context of a boundary layer theory. It was always taken as a model for the entire bulk of the vortex. But we get it naturally here out of this regime. So basically you have gradient wind balance in the radial, you have angular momentum conservation in the circumferential direction, you have hydrostatics, divergence constraint, and here now you have something like heat is driving, similar to WTG, a velocity along the gradient of potential temperature. So here the potential temperature can have a strong gradient, as indicated here, and so you drive a flow in the direction of the gradient. That's what happens here. And again, now, normally the Eliasson balanced vortex model comes with the challenge of solving what is called the Sawyer-Eliasson equation, which is an equation, elliptic equation for the streamlines of this secondary circulation that I showed you. Turns out, people always argue, is the Sawyer-Eliasson equation elliptic or is it not? And it turns out it can locally break down and become hyperbolic. Here it turns out to be completely hyperbolic everywhere. And that means we can solve this by the method of characteristics, and this is how you get beautiful solutions of this almost analytically. If you have conditions near the ground, you can actually integrate the whole thing, and you get it. So that's nice, you can solve this equation. And then finally, this is actually a composite solution of the convection control and friction layer solutions, where this is the friction layer with this turning point, not as strongly as in the previous picture, but that's something Tom produced very recently, the first composite solutions of the two layers together. Why do we call it convection control? It turns out if you model where would the first convection set in, meaning you model the level, the lifting condensation level, which is the surface at which air that comes from the ground would first start to condensate. The water would condensate out. If you model that by getting your potential temperature distribution from the boundary layer, you find out that this lifting condensation level naturally will have some shape, non-trivial shape, and develop it as a function of what happens in the boundary layer below. So that's one. And then once that happens, obviously when parcels move up, first without condensation, but then at this point you suddenly get condensation, you have an effect similar to what we had in our heat up, spin up of the heat law. Particles move up, potential temperature stays constant, and once you hit that level, you get the slope, the adiabatic, what is it called? The Moisen adiabatic distribution of potential temperature. That has a finite slope. And that's what you see here. So that's why convection is actually controlled in that layer. And finally, that's the last slide, and we're working on this. This is not done yet. The numerics of it is under development, but what basically we do here, we solve the equations on top of the convection controlling layer. This is the axisymmetric version of the theory I showed you before, when the vortex is upright and not tilted. That's the evolution equations you get here. It's again, looks like an Eliason balanced vortex model, with the difference that now you have no time evolution of theta, which Eliason had in its original time-dependent model, but you have a WTG approximation for vertical velocity, and the only time-dependent variable is the principal circulation, the primary circulation of the vortex. And this we're solving now numerically. Here's the first outcome of the secondary circulation that Tom produced. And what is mentionable here is non-stationary primary circulation, gradient wind and hydrostatic balances, you have them here. Anelastic motion, now you have to take into account that the depth of the atmosphere is big, so you actually have a substantial change of pressure across the height. And you have WTG forcing. And the coupled solutions, once they're done, the paper is basically out the window because the paper is essentially written except for the results. So I hope to be able to send you that in 2 or 3 weeks. Okay. That's it. So what I did, I showed you 2 theories where a triple deck boundary layer theory was seemingly needed from physical arguments and real observations that imply that something is going on. The history of this actually is coming from here. So we first did the boundary layer theory for the vortex. We found out you need this intermediate layer, otherwise you cannot explain what happens to mass coming out of the friction layer and moving vertically. It didn't fit right into our bivortex theory, so we needed this intermediate layer. But then matched asymptotics requires you to match the vortex to the far field. And in the far field, we only had the QG theory, and that doesn't have an intermediate layer. And then we thought, okay, how do we do that? And then I invented the diabatic layer, and later on we found out, looking at all these arguments I gave you before, that seems to make a lot of sense even without the vortex, to have a diabatic layer in QG theory. And so that's how it all came about. And that was also a sort of a summary, and with that I thank you very much for your attention.
Thanks, Rupert. We have time for maybe a question or two.
So in one slide you mentioned it's very important to have the horizontal vorticity as well in the lower levels.
Yeah.
I may have missed that. Could you explain
Yeah,
more?
okay, I'll go back to where that was. It was basically here. No, yeah, I mentioned it in this context. So what I'm saying is, not that the horizontal, where did I put that? Here, right there. That the horizontal part of vorticity being yielding a contribution to the leading order PV is dynamically important. That's not what I wanted to say. What's dynamically important is simply this. You have a pressure that's imposed on the top of the diabatic layer. Your evolution of the potential temperature perturbation allows hydrostatics to change that pressure again before you can get to the top of the friction layer. And this distribution therefore creates a completely different wind in this region, but at the same order of magnitude than you have it in the QG domain. I was only referring to PV looking differently. The formula for leading order PV looks very differently here than there, to basically relate to colleagues in the room who might be PV thinkers, as they call themselves. So they basically have an intuition about how PV induces flows, etc. And so this is why, another aspect of why this really does something very different than QG. Okay, thanks for the question.
Any other quick questions? John?
I've asked a lot, but I got one more, if you don't mind. Can you imagine a role for spiral rain bands in the vicinity of the tropical vortex? They don't, all tropical cyclones don't have them in the most exaggerated form, but it strikes me that when you're talking about the stability of the heating stabilizing the shear, or what the cyclone can take for shear, do the spiral rain bands kind of produce a stabilizing outrigger structure for the cyclone, perhaps?
So I haven't looked into that enough yet. So I don't know whether in this early stages the spiral bands are there already, because the convection is really very asymmetric in this case. Later on, when they come up, the spiral bands are basically a consequence of the advection around. So basically convection is picked up, it's moved around, and that produces somehow naturally the spiral band. And Mike Montgomery would say it's also a consequence of vortex Rossby waves. This is the same as a Rossby wave in the mid-latitudes, except the background vorticity that's shifted is not the planetary one, but it is the vorticity of the large-scale vortex that gets perturbed, and that produces a kind of Rossby wave too. It turns out that in this regime that we're looking at, the vortex Rossby waves act on a much faster time scale than we're looking at here. So in order to see them in the theory, we would have to do multiple time scale asymptotics. And that we haven't done yet, and Tom is writing a proposal. He wants to do a postdoc and study that. So wait a year or two, and then Tom will tell you more about it.
Okay, great, thanks.
All right, let's thank Rupert again.